Hello everyone! Welcome back to the Physics 170 and 175 lab course. Today we will talk about rotational motion. Rotational motion is quite similar to translational or linear motion. Whereas in linear motion we have a position x that changes with time, in rotational motion it is an angle theta. In this example, theta is increasing with time at a uniform rate. Let's do a quick comparison. For linear motion, we have the displacement coordinate x. For rotational motion, it's the angular displacement theta, or simply the angle. In linear motion, when we move forward, our position x changes at a certain rate, delta x over delta t, and we call that rate the velocity. In rotational motion, when the angle changes, we call the rate of change of the angle the angular velocity, and it's typically written as a lowercase Greek omega. In linear motion, when the velocity changes, we have an acceleration, which is equal to the rate of change of velocity. In angular motion, when the angular velocity omega changes, we have an angular acceleration, typically written as a lowercase Greek alpha. When an object moves at constant velocity, the position changes according to x equals x naught, the initial position, plus velocity times the time. For angular motion at constant angular velocity, we have a very similar equation. The angle is equal to some initial angle, theta naught, plus omega times t. For motion at constant acceleration, the linear velocity changes according to v equals v naught plus the acceleration times t. And again, we have a similar equation for rotational motion. Here it is the angular velocity omega that changes according to omega naught plus alpha, the angular acceleration, times t. What about dynamical quantities, such as mass? Well, it turns out mass is also important for rotational motion, but it's not just the mass itself that counts, but it also matters where the mass is located relative to the center of rotation, as we shall see in our experiment. So the quantity that's approximately the equivalent of mass in linear motion is the so-called moment of inertia. And that moment of inertia is calculated as a sum over all the masses in a system times the distances from the center squared. What about a force? We know in linear motion it takes a force to cause an acceleration and to set an object into motion or slow an object down. In rotational motion, the equivalent quantity is the torque. And just like we have F equals ma, Newton's second law, for linear motion, we have torque tau equals moment of inertia I times angular acceleration alpha. So that's Newton's second law for rotation. Next we look at momentum. In linear motion, momentum is simply the product of mass times velocity. So likewise in rotational motion, we define the angular momentum L as the product of moment of inertia and angular velocity. Finally, the kinetic energy. You all know that in linear motion, kinetic energy is calculated as 1/2 mv squared. And we have exactly the same type of equation in rotational motion. Here the rotational kinetic energy is 1/2 I times omega squared. Now in our experiment, we have a turntable into which we can screw two cylindrical masses. And we can screw those masses either into threaded holes near the center of rotation or near the perimeter of the turntable. If you remember the equation for the moment of inertia, you see that changing the location of those masses will change the moment of inertia. The farther out the masses are, the larger the turntable's moment of inertia. So now we set our turntable in motion and record the rotation with our webcam, and then use video analysis to calculate and plot the angle as a function of time. Now, before we load our videos into Logger Pro, we need to discuss one instrumental artifact called the rolling shutter effect. Look at the two pictures below. The one on the left shows the turntable when it's not rotating. And you see the lines separating the differently colored segments are perfectly straight. The picture on the right shows the same turntable when it's rotating, and magically our straight lines have turned into curves. This is an artifact due to the way the digital image sensor of the webcam is read out. In the lab manual, there's a link to a YouTube video that explains this rolling shutter effect, and that same video is also linked on YouTube below.